Who jumps out of perfectly good airplanes in the name of science? Mr. C.
Okay, 8th grade. Happy downhill day to you, all downhill after today, and then only 2 days left. And then, you know what's going to start? SB spring break. Woohoo! So, anyway, but between now and then, we've got a number of things that you need to put in your journal. So your journal's out, and then you also have out your lesson planner. Your homework tonight is to review for your big fat quiz, BFQ, on Friday, or a small test. 25 points max, I'd say. 25 points. So, hey, good news. I have good news about, I'll come back to the quiz. I have good news about Perseverance on Mars, and you saw this in the video. They tested the wheels to make sure they would turn properly. I think they turned like 30 degrees each way, which is what they're supposed to do. And then they traveled a number of meters to make sure that it would move, the wheels would move okay. And then they backed up and took some photos, and they were extremely pleased, even better than they thought, about how the motors that actuate the wheels worked and just how it moved. So it's all good news. Yay, Perseverance. Okay, I wanted to show you this and explain something about Mars and Earth and the Moon. This would be a meteor. Now, it could, you could say, well, it's an asteroid. No, but it was a meteor. Okay, there was a fairly large meteor. It was either last night or the night before, that crashed into the atmosphere over Vermont at about 40,000 miles an hour. It was going so fast, and there was so much friction with it, and it was large enough to cause a big explosion. People could hear it on the ground. It broke up in little bitty bits, and I don't think any of those little bitty bits made it to the ground. They all burned up. It was going so fast, there was so much friction, therefore so much heat, and it ended up probably just vaporizing all the meteoric particles. So anyway, and caused quite a stir. Seismographs on the Earth that measure ground shake actually notice a little bit of shaking. Not enough for humans to notice, I don't think, but the explosion they heard that. Anyway, I want to make the point, on Mars, hardly any atmosphere, 1% of Earth's. So a meteor like this would hit the ground and make a big hole in the ground, aka crater. Okay? On the Moon, the same way. On Earth, no. Burns up. We've got a shield. So our thick atmosphere of nitrogen and oxygen is a nice shield for us. Part of Earth's just right. So thank you, Lord, for the protection. So I wanted you to see that. So, and then I've got a number of other things I want to show you. Okay, I think I'm getting them ready. There they are. Oh, beautiful. Yeah. All right. So if you will take out your evolution pillars chart, as usual, on Wednesday's homework notes, I'm going to list the topics that are going to be on Friday's BFQ, Big Fat Quiz, or small test. So 25 points-ish. Yep. So what's going to be on there? Well, first, guaranteed, I am going to ask you about the pillars of evolution. So do you have your pillars chart out? Now, we've got a number of extra copies on the white shelf, and if Mr. Phillip would help out with this, if you don't have one, if you'd raise your hand, you probably want one of these in your possession. So, and since it's 25 points, I may or may not ask you for what probably will, what the pillars of evolution stand for. Foamn plus B, right? F-O-A-M-N plus B. Fossils, old age, accident, mutations, natural selection, and Big Bang. And I'm probably going to ask you for some data, some scientific data, that actually says each pillar doesn't work. For instance, the fossil pillar, no tweeners, no ape men, They should be there if evolution happened. In fact, those fossils in the Earth's sediment layers are evidence there was a great global flood that buried them rapidly in sedimentary rock that didn't erode in between the layers. So it had to be laid down really quick. So, and then you know about the dinosaur fossils that still have DNA in them, or they don't have enough minerals in them. They haven't hardened enough because they haven't had enough time. Or they have red blood cells in them. It should have all broken down in a few thousand years. What does it mean? Those fossils aren't that old, and it would be in keeping with the great global flood, who knows, 5, 6, 7,000 years ago. So, and not millions and billions of years ago, like evolutionists say. So that's the fossil pillar. The O pillar. O pillar, evolution requires billions of years. What if there is evidence, science evidence, that it's only thousands? That's a massive problem for the evolution idea. Like, for instance, the sun's too small and not bright enough. If it were billions of years old, it would be way bigger and way brighter. It's just right for us. It's a just right. Proves there's a God, actually. So put it just the right distance, just the right mass, just the right gravity, just the right amount of fusion, so, and just the right amount of heat and light that it produces, and a bunch of other just rights as well. So anyway, we've got just the right size sun, but it doesn't match the evolution idea. Then I've already mentioned the stuff in the dinosaur fossils. Then the Earth's too hot, the Moon's too hot. They should have leaked their heat out a long time ago. And comets keep coming back. They should have all melted a long time ago. So all these evidences don't match the old age idea. The A idea, accident idea. Evolution's an accident. No one did it, supposedly. It doesn't work. Because the law of cause and effect, things don't happen by accident that are complex or ordered. They've got to have an ordered cause. If you've got a design, of course, you've got to have a designer. Something that's made, a maker. An invention, an inventor. Okay? A computer program, a computer programmer. DNA, which is a computer, not a computer program, but a program. You got to have somebody that programmed it. Programmer. The great programmer is God, of course. And he programmed DNA, and it's just terrible evidence against evolution. Remember the geneticist who said, I don't know any geneticist that I work with who believes DNA evolved. They believe it had to be designed and created. So anyway, then you've got mutations, which are bad. They're supposed to cause good changes. Billions and trillions of them over billions a year. No. They're bad, they're harmful, they're rare, or they're even fatal, lethal. So anyway, it doesn't work. Natural selection doesn't make things change. It gets rid of evolution. An evolutionary scientist said, no matter how numerous they may be, mutations don't produce any kind of evolution. So the two mechanisms that they propose to make evolution happen don't work. It's like this. It's like the red Ferrari I showed you yesterday, that's advertised to be really fast and really great, but it's got no engine, so it doesn't go anywhere. It doesn't move. It doesn't work. That's a good analogy for evolution. Okay? So I just wanted you to see that again. So those are the evolution pillars. Okay? So now I want to, you already read about this and studied this, so I'm going to show you this. This is going to go in your journal, right? In your journal, like right now. Okay? These are the principles about gas. You read about these. Gas principles. So number one, you're going to put a T and show an arrow going up. Every one, it's not an option, 8th grade. If T increases, then so does P, or pressure. So when you've got a gas, if you heat the gas up, its pressure or its force, how hard it pushes against other things, goes up. I'm going to show you an example of that in just a minute. Next, if T goes up, volume goes up, TV. So you've got T goes up, P goes up. And then if the temperature goes up, the volume goes up. So it takes up more space. And here, I hope I still have this. I think I do. Here's a great visual of this very thing. It's a hot air balloon being inflated. So they're heating up the air inside the hot air balloon. What does it do? If its temperature increases, T goes up. What else goes up? The pressure of the gases. So the gas pressure starts pushing on the inside of the balloon. And then TV. If the temperature goes up, the volume goes up. So the gas takes up more space. It's got a lot more force. So it fills up, it forces the balloon skin out. Inflates the hot air balloon. Thumb up if you've ever had a hot air balloon ride. Mr. Phillips, noticing. Ever been on a hot air balloon? My daughters have, I haven't. So anyway, that's the example of two of the gas principles. T goes up, what goes up? P, pressure. If T goes up, temperature goes up, what else goes up? The volume takes up more space. It expands. So, and the opposite happens if it's cooled down. Takes up less volume or space, and it has less pressure if the temperature drops. So the reverse is true. And then the third gas principle is this. If the pressure goes up, see that? Then V goes down. Volume goes down. So if you squeeze a gas into a container, you squeeze a gas into a container, it takes up less space. Volume goes down. So if, in this case again, the pressure goes up, so you squeeze that gas, it takes up less space. Volume goes down. So pressure goes up of a gas, volume goes down. Did you get those? I'm going to show them to you again. Make sure they're in your journal. They'll be on the BFQ on Friday. There they are, all three. Make sure you've got them. Mr. Phillip is encouraging that right now. Temperature goes up, pressure goes up of a gas. Temperature goes up, volume goes up. Pressure of a gas goes up, it takes up less space, so volume drops. Okay. Now, do you have an example of that? I do. Here it is. Maybe. If I can get it to come. And it looks like it might be coming. I might have to describe it to you. Here it is. See the scuba tanks? So they squeezed oxygen into these scuba tanks. So it took up less space. So the pressure of the oxygen went up, P went up, volume went down. And it was squeezed into a smaller space in these scuba tanks. Thumb up if you've ever scuba dived. How about you, Mr. C? Once. I did this. This is a basic scuba dive. On the Great Barrier Reef in Australia, I went down 15 feet to the bottom. And just breathe a little bit and all that, and sort of got used to it. I actually never got used to it. And I had a phobia about it. What's a phobia? A fear. I don't think I'd ever be scuba certified. Why? And I can't explain it to you. We all have phobias, right? Different phobias, maybe. Some of you don't, but you're fearless. Okay? You maybe need to be a little bit more afraid of things because you might hurt yourself. So I have one grandson that's fearless. He just does crazy things and, he's not afraid of stuff. So I have another grandson, my oldest grandson, who's like me, more cautious. Well, I didn't enjoy the scuba experience. You know what my worry was? Somehow that the tank would quit working and I wouldn't be able to breathe, and I'd go to heaven. So will I scuba dive again? No. Will I snorkel again? Sure. I love to snorkel. Why? You're on the surface with your tube. your air tube on the surface. I love to snorkel. How many times have you snorkeled? In Hawaii and on the Great Barrier Reef, I don't know, 100 times. Bunches. I love it. I love seeing tropical fish. It's just fun, fun, fun. So I love it. Okay, what else you got for us? I've got to check. And I've got to check the time too. Okay. Doing good. Doing really good. I wanted to explain to you the other day in the snow leopard video. In the snow leopard video, I loved it. I loved all of the divine designs of the snow leopard, and it obviously couldn't wait around for all of that equipment and its instincts. It would die in the really high, low oxygen, low temperature habitat. So anyway, I mean, God had to make it, adapt it. Now, I want to explain the word adapt. They use the word adapt in the video. Sometimes that word adapt is used as a code word for evolution. It would be like this. This would be the evolution idea of adapt. It would be where all animals gradually change to match their environment or habitat. That could not happen because it's too slow and they'd all die. If they don't have their equipment and their instincts right, bam, now. So that can't happen. But when God created animals, different kinds of animals that it mentions in Genesis, and when those different kinds of animals that were caused to come to the ark came off the ark, did they have DNA as they mated that would produce different species? Sure. And that's a kind of adapting. So there'd be all kinds of different species that some would fit a little bit better this kind of habitat or that kind of habitat, but it's not like they would totally not match any habitat. They would die right away. They'd die off. So that doesn't make sense. So is there room for slight changes or adaptations? Sure. Yep. And it's in the DNA that God built from the beginning. So it'd be like you start with big cats and you end with big cats. But in the meantime, could you have in their DNA the production of, say, lions, tigers, and as the animals that came off the ark, the kinds of animals that came off the ark mated, the big cats. Sure. So same with all the different animals. So they had different DNA that would produce that. Okay. So I wanted to make sure that I went over that and I told you about that. Now, I guarantee I'm going to ask you the foam and pillars, so you'll study that. So I'm going to ask you about this. I'm going to ask you again about parts of an atom. This is a helium atom. 2 protons in the nucleus. Some of you thought the center of an atom wasn't a nucleus. It's a nucleus. So protons are in the nucleus. So a helium atom, 2 protons, 2 neutrons, and 2 electrons. I'm going to ask you about the forces that hold atoms together. So what are those forces? Opposite forces attract. Some of you missed that on the test, recent test. Opposites attract. So electrons are held in by, the electrons, negative charges, the protons, positive charges, attract each other and help to hold the atom together. But the thorny problem is those protons in the center. They're the same charge, and like charges repel, force or push each other away. Now I ask you that on the test. Only a handful of you got it. I hope all of you will get it this Friday. Why do protons hold together in the nucleus? What overcomes the repulsion force that should happen? There's a really, really cool force that's evidence of God's design that overcomes the repelling force. It's stronger than that. And that's why it's called the strong nuclear force. SNF. Strong nuclear force that holds protons together in the nucleus, or the strong force. So I'll ask you about that. Okay? You can expect that. Now, you did some homework about the different models of an atom. The models of atoms have gradually changed over the last only 100 years or so, a little bit more. So most of history we didn't really know about how atoms work, and we still don't really. We don't exactly know how they work, but we know some things about them. So checking the time, I want to make sure that I save enough time. So I'm going to see if I can find this. You now know that we have gradually come to think that an atom is like a cloud because of the way the electrons are moving really rapidly. In the outside part of the atom, you can't really see to the inside. It's like a cloud. And you now know there are a whole bunch of different subatomic particles. Like, I haven't even told you some of these. I have a full list of these. You already know about protons and neutrons and electrons. But here's some other particles. So there are muons. There are tau neutrinos. There are BOSON, bosons. So there are photons. There are Higgs boson particles. There are top particles, bottom particles, what are called charms, strange particles, down. These are up and down particles. So there are a whole bunch of different particles now that are smaller than the whole atom itself, subatomic particles. So anyway, I may ask you something about that on Friday. So tomorrow, in our half day, like 28-minute period, we'll review. You review tonight. That's your homework assignment. Now, I'm going to show you a video. It's perfect. It's going to get us to about the 30-minute mark. It's about atoms. And then after that, you might have a few minutes left. Mr. Phillip will answer any questions that you have. And then he might give you a little time to review to Triple R on your own. So anything you hear tomorrow, stick it in your journal. Anything that's new that's not in your journal. So study the pillars of evolution, Triple R those. Study the parts of an atom, study those. Are you going to ask us the elements that you've learned so far? Yep. O2 for oxygen, N for nitrogen, H for hydrogen, He for helium, don't get those mixed up, He for helium, carbon for living tissues, carbon atoms, and then iron atoms, Fe for the metal that's found on Earth and also on Mars. Okay, a short video, about 6 minutes, perfecto. So I think you'll find it interesting. Anything you don't have in your journal, stick it in there. Okay, I will see you on Thursday. Mr. Phillip, take it away on that video.